Okay. So ignore the time in the upper left corner, 3:52 a.m. I fell asleep early and woke up around 2 in the morning, and it's kind of like one of those things where you just had enough sleep that you're just not going to go back to bed. So yeah, I'm just kind of sitting here in the middle of the night making physics videos, so enjoy. Here we have a situation where I'm gonna use this problem. This is assigned for Monday. To introduce the concepts of x and y components of momentum, and then the fact and the conservation of momentum in the x and y direction. So here we have sort of a common problem that's used for x and y momentum, which is a billiards problem. So you can imagine that this ball is going to hit somewhere off center. Maybe I'll make that a little bit darker here. It's going to hit off center. So even without looking at the second picture, you can imagine that this object is going to go off somewhere in this direction here, and this cue ball is going to go off somewhere in this direction here, right? So you can just imagine that that's what's going to happen. And in fact, if you look at the next picture, they give you some more precise information about it. And they give you the initial masses, or they give you the masses and the initial velocities. And then, in fact, they even give you the final stuff. So this is going to be kind of a sort of an easy, low-level x and y momenta question. I have, I think, more interesting questions that I'll get all assigned for Tuesday after I've introduced it today. Okay, anyways. So it says calculate the x and y components to the momentum of these two objects before and after the collision. And then we're supposed to write those down on the chart down there. So let's just get started with the first one. I think I'm going to do this up here a bit. So this first one right here, that's the momentum. So momentum in the x for the first object. It's going to be m vx. Now the m in this case is 1 and the v is 16. So it's going to have 16 kilogram meters per second of momenta in the x direction. Okay, so that takes care of that one. The y momentum is easy. It has none because it's only moving in the x direction. So P1y is just simply 0. So I can fill those in right now. So this is going to be 16 kilogram meters per second, and this is going to be 0 kilogram meters per second. Let's do this one right here. Well, that was a velocity of 0, so guess what? That's going to be super easy. 0 kilogram meters per second, 0 kilogram meters per second. All right. Now it's after the collision. So you can see after the collision, the first object has momentum now in the y direction like this, and the second object is going to go off at an angle right here. So this is the key idea now, is that this second object has momentum in both the x direction like this, but it also has momentum in the y direction like this. Because, again, momentum has a velocity vector, and velocity vectors have x and y components. So let's do the first one here. This is the easy one. The momentum of the second object in the x direction finally is going to be 0, because if you notice, it's only going in the y direction. The momentum in the y direction, it's all in the y, it's going to be 12 kilogram. Oh, sorry, let me stop that right here. It's going to be m1v1 final, which is, now in this case, we got to be a little careful because this velocity vector is a negative 12. It matters because you have the second object going up like this, and you can't confuse that velocity vector with the velocity of the first object. So we got to have a negative 12 right here. So negative 12 kilogram meters per second. Okay. Now for the second object, it's a little bit, not too difficult, but it's a little bit more involved in that. Here we can see that the P2x and P2y, that the P2, let's go x first, is going to be m, which is 4. It's going to be v cos theta. The v is 5, and cos theta is 37. It tells you to use 0.8 for cos theta, so it's going to be 20 times 0.8, which is 16 Okay, so this is going to be the px, the momentum in the x direction for this first object, or sorry, the second object. And I guess I'll just do it over here since I have not that much space. The p2y is going to be mass times v sine theta. It tells you to use 0.6 as sine 37, so 0.6 times 20 is going to be 12. So that's going to be, and this is going to be a positive 12, again because the velocity vector is positive. Now we can go down here. What is the after collision momentum in the x direction for the second object? It was, survey says, positive 16. What is the y momentum collision? Negative 12. I'm sorry, positive 12, positive 12. Yeah. That was the second one I was looking at, not the first one. So that was for the first object after the collision. So 12, positive 12. And the reason I made that error is because I should have been a little bit more careful when I labeled these things. This is actually 1. Right? It was 1. I was thinking of 2 to mean final, but that's what happens when you mess up with your subscripts. All right. So now it says, show using your data that you listed in the table that linear momentum is conserved. Okay, the total momentum in the before the collision is 16 in the positive direction. In the x direction after it collides, the total, all right, so this is where we got to be careful. We're adding down this way. All right. It is 16 before, and it is 16 after. Now we could take a look at the y direction momentum was originally 0 because it had 0 here and it had 0 here. So it had 0 total. So this and this together also equals 0. So I guess we got to be a little careful how this is sort of a weird table how it's laid out here. I would definitely not have laid it out the way that they have, but it just takes a moment to look at. But yeah, I'm going to make this a little darker here and use blue. In the y direction, it has to equal 0. Negative 12 plus a positive 12. Again, to show you that this thing right here had 0 in the y direction, and this one has a negative 12. This one better have a positive 12. In the x direction, this one had 16 in the x direction. So this this total must here better be 16, and it was. Again, definitely not the clearest labeled table or the way that they laid it out, but it just shows you that the momentum is conserved. Okay, calculate the kinetic energy of the two-object system before and after the collision. Okay. Total kinetic energy of the system, well, Ke before is going to be 1/2 m1v1 squared plus 1/2 m2v2 squared, which is going to be super easy. It's going to be 1/2 1. What was this velocity? Was it 16? It's been, yeah, 16. Now, the second object is motionless, so that's easy, 0. 16 squared times 0.5, 128. So 128 joules of kinetic energy in the system before the collision. Whoopsies. After the collision, Ke final. 1/2 m1v1 final squared plus 1/2 m2v2 final squared. This is going to be 1/2 1. The velocity now of this object at the end was 12. And this one, the velocity was 5. So, what's half of 144? It's early, so I'm just, 144 divided by 2. Darn it, keep hitting the wrong button. 72. So 72 plus 25 times 4 times 0.5, 50. Looks like 122 joules. Okay. So, that is the after the collision. Is kinetic energy conserved in the collision? No, it is not. The kinetic energy is not conserved. However, the momentum is. So, no, it is not. So, this was an inelastic collision. It doesn't ask you to write that down, but it's inelastic because there was some energy loss. And in real life, that energy loss would be due to the sound waves that's created when one ball hits the other ball. There's some vibrational energy. The balls shake a little bit. And so there's energy loss at that level. And that is how you do conservation of energy in the X and Y direction.